to do here. Thank you. So I'll try to answer most of your, I would say, technical or implementation questions, both in terms of the performance of Ultrasat and including also the modes of operations. This is maybe the summary slide of the first part of my talk, which is how Ultrasat is being implemented. I'll briefly go back on what Eli said. The spacecraft will be produced by the Israeli aerospace industry. At the heart of the spacecraft, we have the Wide Field UV Space Telescope by ELOP. And at the center of that, we have the DESI camera. And I'll go through each of those components and give the details that we currently have on them, or the requirements. For some of the components, we still don't have actual measurements. And at the bottom, you can see the timeline. We do plan to launch in about 4 years from now. We wrote end of mission in 2028. This is the minimal end of mission. And in the next slide, I'll start to explain what I mean by minimal. So we'll go from outside inside. I'll start with the spacecraft. So we are launching into a geo orbit. We'll be placed on the slot 4 West, which is an Israeli slot. This is still under discussion, but this is most likely the place that we're gonna be at. We will do full station keeping, meaning that we're gonna be at geosynchronous orbit, not without any drifting at the north, south, or obviously east-west. And the mission lifetime is 3 years. However, in terms of fuel, we have fuel for 6 years. So the requirements on the reliability of all the components of the spacecraft is 3 years. But if nothing breaks, we can go for at least 6 years. And this is the current plan. Following Danny's question, so the minimal time availability for science will be 90%. The current estimates are, by the way, almost 95 or 96, but this might drift back. This is the requirement. So we're gonna enforce that. Being at geo orbit allow us to have continuous transmission. So all data will be transmitted to the ground all the time and being analyzed in real time, except of about 13% of the sky that due to the antenna limits, once we are pointing to that direction in a TOO, we cannot transmit the data in real time. We can store the data for much more than 3 hours, which is our expectation for TOOs. So later we obviously can transmit all the data. In terms of slewing ability, so we can, first of all, we can observe 50% of the sky at the worst case. The worst case is of the spacecraft being exactly in the middle between the sun and Earth. So we have both limitations, but in other places, we can observe more than 50% of the time. It will take the spacecraft to slew to any position within 10 minutes. We require 15 minutes because we also have 5 minutes to analyze let's say the trigger by the gravitational wave, see if it's relevant, pass it to IAIs. They will plan the slewing path. And actually, after 15 minutes from a trigger that received here at Weizmann, we can start to observe. For at least 3 hours, the actual limitation for the 3 hours is, as Eli said, is power. So it's not the same direction, but it's still the same number. So 13% of TOOs will be without the sun hitting the solar panels. So we cannot observe more than 3 hours, but our battery allows us for 3 hours of observations. Now, the other thing that I want to say about the spacecraft is that the jitter of the spacecraft, the pointing stability, is less than 3 arcsecond, 3 sigma over 1 exposure strand a second is our default exposure time. And it is designed like that, or set like that, so it won't be the dominant factor of the PSF. We'll see later the optical PSF, it's not as good as that. And this requirement meaning that this is not the limiting factor. You can see here just a blowout of the spacecraft. I won't go into the details of all those components, just showing you that we are in a very advanced mode of the design, actually hopefully finalizing the design in the next 3 months to 6 months. And that's it. Now, at the heart of the spacecraft, we have the telescope, the optical design of the telescope was done by Sagi, along with ELOP, which are producing the entire telescope. The aperture is 33 centimeters. We have a Schmidt-like design with two correctors at the entrance, followed by a single mirror, and going into back into, show it, into two flat field lenses, which are just in front of the camera. Each pair of these lenses is composed of both fused silica and calcium fluoride. This allows us, first of all, these are the transparent materials that you can use in UV. And with that, we can have both wide field and correcting for chromatic effects, as I'll show you later. We will have a focus mechanism. It's still not decided yet if it will move the flat field lenses or the mirror. Most likely it will be the flat field lenses. It will somehow lower our, or make our obscuration larger, but this is a more robust capabilities that ELOP has now. Now, in front of the telescope, we have a very large baffle. I'll give you some details about that in 2 slides, but the main 2 targets or goals for this baffle is first to reduce stray light and to minimize it, so this won't be the dominant factor in our noise sources. But moreover, because we are in geo orbit, we are in a region where we have trapped electrons, and when they hit the Schmidt corrector, they produce UV radiation, which actually, even after this big baffle, is comparable to our dominant factor in our noise sources, and I'll show it later. Because we're observing the UV, we are highly sensitive to contamination. This means that the entire telescope and the baffle is made out of with no complex material. We will have several outgazing cycles, both obviously on ground and before starting the observation, but also periodically, once we'll see some degradation in the image quality, we will have some outgazing cycles. Yeah.
So the baffle is going to stop those electrons?
It will. I'll show you later. First of all, yes, the walls will stop them from hitting inside, or at least most of them, and it will mainly reduce the solid angles that you can see. So those that will come directly there, you will have that, but we will. They won't be the dominant factor. I'll show it in like 2 or 3 slides.
Maybe
Sure.
So the baffle would also be made thick,
yeah,
so that it would have enough grammage. It will not be just a very thin light reflector. It would be a bit thick.
So then it could just cause showers that will just magnify your.
Okay, so the main problem is the lower energy electrons, and you need to stop them. The lower energy, you're dominated by the lowest energy electrons. And as the energy of the particle is lower, the path length is much shorter. So if you start with some energy electron, and if the thickness is large enough to stop it, all its daughters would also be stopped. You would still be left with the higher energy one, but the flux drops exponentially with energy. So
okay.
I hope we did the calculations right.
Obviously, the design is to optimize the PSF for a large field of view and in our observing waveband, which is 220 to 280 nanometers. Nevertheless, we do still have some radial variation of the PSF and wavelength variation. And you can see it here, the bottom low panel. This is our PSF. You can see here the scale of the full F max as a function of both wavelengths and distance from the center of the corrector or of the camera. So we have regions where we are actually undersampled and regions where we are critically sampled or a bit oversampled. But what this means that we will have varying PSF as well as a chromatic effect. So you can see at the top our optical throughput. It is optimized to our band, passing over 80% within our band, and have about 0.4 or 0.5% subtraction of out of band, but still very red stars or very red sources will have this red leak and made our PSF larger. So In some sense, it also allows us to fit for that and get the color of a source, but this actually makes for red sources contributing both to the noise and makes their PSF larger.
Can I just correct you on one thing?
You can correct me on more than one thing.
It's actually, but just to give the proper credit, it's not my design with LO building it. It's a joint design of LO and myself, and we work in a very strong collaboration. I think quoting LO, it's the strongest collaboration they ever had in terms of the actual payload design with any partner in the past. And that's part of the key goals, I think, of such a mission, is actually to establish these connections between academy and the industry.
So Guy is modest as always.
No.
That's fine. So this is just a list of the parameters. I went over most of them. Very wide field, 200 square degrees, 300 centimeter aperture, less than 13 arc second. Actually, the mean is around, currently is around 11, but 13 is the upper limit. And that's it. Obviously, as Tzvi asked, all of this information will be online. Most of it is already on our webpage, but this presentation will be online, so you don't need to remember all the fine details.
Yossi, is there?
Yeah.
Did you try, or is there no way to get better, more suppressed red leak? That's not very good.
That's not the red leak, that's the full width.
No, he's talking about the suppression here, right? So this is actually very, very hard to achieve. The only thing that I would say that this is before the quantum efficiency of the detector, which will give us maybe another factor of 2 or 3. But with the current coating that we have, that ELOP have and the best worldwide, this is what we can achieve.
How does this compare to Galax?
Galax was UV solar blind, basically.
I know.
Yeah, but Galax had 10% efficiency. This is in that. You sacrifice a lot by going to
How about the UV filters on HST or JWST? Are they comparable?
Sure, it's much better.
This is better?
No.
Yes.
My suspicion is that they lose also the efficiency, the in-band efficiency of the.
So the issue is that you want to keep 90% in-band, okay, and strong suppression out of band. So you need to look at the combination and the spectrum of your background. So this is much better.
Also, in terms of the angle of incidence, because of the large field of view, you are going into the optics at very high incidence angle, and that makes very, very efficient filters very difficult. So it's a physical limitation.
Danny, why do you afraid from red?
Because you have in the R band you have a 1% transmission. Okay, so anything that's 100 times brighter in the R band than in the UV is going to dominate.
Right.
So yeah, but this part is clear. So why this is bothers?
It'll make the data almost useless.
So
why?
No, you're looking for transients then.
If that's all you're looking for, then okay.
No, but
for
why
any other science where you're going to measure things.
First, if you the PSF.
You know what the element is.
first of all, the PSF there is about 50 arc seconds. So it will have a lot of flux, but it will be very spread. So it will add to our background. But actually, the heart will still be dominated by the UV in your PSF. So we are actually in the process of producing this artificial PSF as a function of spectral type or whatever you want. But this is something that we need to live with, addressing the two main key aspects of the mission, which drive all of our...
All I'm saying is that the worst that this is, and I accept that this might be as good as you can do, and you've thought about it. But I'm just saying that this will cause photometric calibration problems.
Correct.
When you want to do real photometry in science, you have the combination of the leak from the background and the leak from the source, And with these kind of numbers, for things that are not very blue, you're going to end up with large uncertainties.
But you have all the information. This is,
You don't know.
from ground-based observation, or just
You
from
don't know what the background spectrum is.
On that
the
same
background
subject,
spec?
do you have simulated images including this effect?
So not yet. As I said, we are currently working on that. So we did it for single stars, still not fully images. So
To be honest,
with,
we should also emphasize that we are still working with the lab in developing better and better.
yeah, but it won't be a factor. It won't be an order of magnitude lower. It might be a fraction of 2 or 3 lower at best. So we shouldn't expect more than that, and we should know what we have. The key thing that I think that for many, again, for detection of transient, this will be sufficient. For characterization, would probably want to have follow-up observation from ground. Once you have that and you know the spectrum, you can correct for your photometry. So it's a round. So briefly talking about the buffle, we said one of the main goals is the Cherenkov radiation. What you can see here is that it actually have a large temporal variation of several order of magnitudes, and if you can see it here from a paper by Crook comparing for a geo orbit. In our wavelengths regime, actually the Cherenkov radiation is dominant over the zodiacal light if you don't have any buffer. And what we require and the design for the buffer is such that the solid angle suppression by having this buffer will have a factor of at least a factor of 6. Currently, it's a factor of 10, but factor of 6 is our minimal requirement. And with that, actually, both the Cherenkov and the zodiacal light are comparable. And when I say the Cherenkov, it's 75% of the time of the time of the Cherenkov. You still have some eruptions that will be higher than that, and actually, if you take the mean, it will be much lower than that. And as Eli said, we have a requirement on the column density of the buffer in order to suppress the electrons that are coming from the side, at least the low energy ones. The second thing is about pointing and stray light. So the top of the buffer is slanted at 20 degrees, and this is in order to prevent any sunlight going into the buffer. Any sunlight that actually hits inside the buffer will dominate the entire background of the image. So we can point up to 70 degrees off the sun. For Earth and Moon, we do allow them to, we can point such that their light will go inside the buffer, but still not hitting directly the corrector. And we can point up to 48 degrees from the Earth or the Moon. And with that, the coating of the buffer and the optical path will have a very large suppression factor, about 10 decades of suppression of the stray light. With that, it will make the stray light not the dominant noise source, but actually an order of magnitude below both the Cherenkov and the zodiacal light. Yeah.
These electron events, how frequently do they hit the telescope?
All the time.
What's the rate?
So we have all of this. You can see here their rate per day, etc. I don't have here all the.
It's huge. Squared,
Yeah,
so.
Yeah. It's huge, and it's all
like
the time.
A million a second or something on the whole telescope.
Yes.
Yeah.
Or
well, without the buffer.
yeah.
So. Okay. Now I'll move on into the.
Sorry.
Sure.
I can.
Unless it's directed to that, maybe I'll finish if it's directed to the buffer, then you should ask here.
Yeah, well, you know the high energy electrons that do go through this thing, you know, they're much rarer, but then they produce. I imagine they produce showers with even more Cherenkov light. So won't they still be a bother?
No, they don't produce more Cherenkov light. The energy, most of the electrons that are being produced when a particle loses energy, most of the electrons that are being produced are at tens of keV, and they are below the energy threshold for Cherenkov emission.
But if they started at very high energy
Right.
electrons.
So you're looking at the, so we talk what you look at therefore is the energy flux that you have, and the energy flux is much lower at high energy.
I know, but each of those events produces more electrons that do make Cherenkov light.
Right. So take all the energy of those electrons and put it. Let's
I'm just asking whether you took account of this multiplication factor.
But the maximum you can get
but let me explain why you should not worry about
We're
this.
not together. I can't listen.
So take the energy of the high energy electron and just distribute it all into electrons above the threshold. Okay? You still have orders of magnitude lower than what you have in those electrons, right?
Right.
Because they're suppressed very strong. So their contribution is negligible.
There's no multiplication. It's a fraction. Only a fraction of the energy of a high energy event goes into Cherenkov, because some goes into other.
Okay. At least for now.
Is there any experience with this from other UV telescopes?
No.
Not really.
How come?
So there was only one UV at GEO, IUE, over 30 years ago, and we are actually in communication with them, but they didn't have a Schmidt telescope, so they didn't have this problem. There are instruments that actually measure that at GEO orbit. This is how we have this information, but they are not space telescopes. Yeah. So.
UV, there was no telescope in GEO, except for the two UV satellites.
This is what I said. There was a UV space telescope almost 30 years ago. Okay, now I'll go into the heart of the instrument, which is the camera. As we said, this is developed and supplied by DESI. The actual sensors are backside illuminating CMOS by tower. They are divided into 4 quadrants. Together, the photosensitive area is 90 by 90 millimeters. It is a new camera. Okay, it's a new sensor, and we have support by Ramon Space, or an expert from Ramon Space, designing such sensors to be radiation hardened, to be able to live at GEO orbit. And we are optimizing the UV coating such that quantum efficiency will be larger, and I'll show a slide on that. My next slide will show you that. The main thing that you can see here, the entire spec, I want to emphasize maybe 2 things which are not, I wouldn't say they're not common, but they're not the standard that everyone is usually think when they think of a camera. First of all, we are in a rolling shutter mode. This means that we read each row and start the next integration. So we have, in essence, we have continuous observation. We don't have readout time. It's a millisecond, so it's negligible. However, we do have time difference between the rows. So we have about 15 seconds between the first row and the last row. So we do take this into account, and this information will be provided in the header of the images, etc. The second thing is that we have dual gain.
So the exposure will vary effectively?
No, it's the same exposure, but the exposure time, the start time is
easier or is the line dependent?
Again, locally it will be very small difference, but over 10,000 rows.
Is this how our cell phones work? The cameras on our cell phones?
Not necessarily. Some of them maybe, but not all.
No, most of them.
I think most, I think global shutter, but I'm not sure.
The other one?
You just take a picture of the fan and see smooth. Most cell phones don't know.
But you don't really see the actual image. You see really processed by
Machine learning.
yes.
The second thing,
It's a trade-off with
the second thing that I want to emphasize is that we have a dual gain. So we actually have one gain, which the engineers call high gain. I would call it low gain, but at the low flux region, we have one gain, and the higher, and then we open another transmitter, and we have at larger fluxes a larger full well capacity. and with a different gain resolution. However, we cannot pass this information into the ground, or more correctly, I would say we cannot pass both values. So the only processing on board will be to select for each pixel, do we pass this one or this one, and obviously give a bit saying which one we chose. So, and again, this information will be provided in the raw images. Actually, maybe Ran will talk about it later, but in the processed images, we will already correct for the gain difference between those.
So you may have, you will have a resolution, the precision will be pixel dependent.
It won't. It will be flux dependent. So for each pixel, you can have that and that, but
No, but
conceptually,
in
yes.
Image,
Yes.
every pixel will have a different gain.
Yeah.
So a different
And again, as you can expect, most or almost all will be at the low flux region, and when you have the higher one, and we select the gain accordingly, so your statistical noise, Boston noise won't be the gain won't be your dominant factor. This is how we selected those values. About the coating, so we are examining three coatings, three UV optimized coating, one of which is an already proven and industrial UV coating by Tower, which is this orange curve here. But we do have, or Tower developed two UV special coating for us. These are this blue and red. After we're going to examine them, see that actually these are obviously not measurement, but theoretical computations. And if they are like that, we will be able to choose between them. You can see the difference. One is, the blue one is maybe more optimal for our entire range, and its total quantum efficiency is larger. The second is a bit more with a peak, with a larger peak, and maybe we'll see that this actually gives us better performance. Also, after you including the optical transmission of the mirror and lenses.
Are these coatings essentially down converters, or there's something else?
No, it's AR coating. They are not down converters.
AR. So, but these CMOSs, their peak sensitivity are usually in the optical, not in the.
No, this is the coating.
I understand, but under the coating,
So it's almost 100%. So it's almost 100% photon to electron conversion.
The silicon.
Yeah, I said it's KD electron.
The issue is
I'm asking why it's not a problem, because
The main reason why you have such a big difference is the difference in the index of refraction as a function of wavelengths that grows when you go into the UV. Therefore, a regular loss, the naked loss of an uncoated piece of silicon when you shine it with UV light is much greater than in the optical, because the variance is much bigger in the index of refraction. It goes like n squared.
I understand that, but I thought that the depth within the silicon where the photon is absorbed is also an issue.
But those are back illuminated, so the overall the detection area is very, very thin. You are not being absorbed from the gates.
There is another problem related to this, which is the accumulation of electrons near the surface because of the UV short wavelength absorption. So you have to deal with that too. And this is dealt either by the process we want to do first with the JPM, or by what Tower is doing, and they have some high KD electric coating that prevents the accumulation of these charges next to the surface. And this prevents degradation of the efficiency when you accumulate flux from the detector.
It's part of the thinning passivation process that Tower has, I guess, defined for data.
I guess it's too late in the planning stage, but instead of choosing...
No, with this out, you can say whatever you want.
But instead of choosing, did you consider a Fisher field? Then have both options?
What?
No,
So the sensor is 400 micron of the lens. You don't have any place to put anything. You just coat that and that's it. Very briefly, I'll say about the launcher. We have two options. We actually are supposed to get any day now the options from NASA. Either go into a direct launch into geo orbit, or being a passenger over a larger satellite that will be injected into GTO and then moved to geo. Once we are deployed, we probably won't be at far west, and we need to drift into our locations. So this might take about additional 6 months. So after launch, up to 6 months will be before we start normal observations. I'll skip this slide, just saying we have continuous communication through IAI into Weizmann Institute and the opposite way, obviously. This is the program timeline. You can see that we are now in the middle of the reviews or the design phases. We passed the system and requirements and design reviews. We are before the preliminary and critical design reviews. You can see here when actually the camera is being supplied from DESI to ELOP, the payload from ELOP to IAI, and we will be ready for launch in the second quarter of 2024. Okay, so this was about the performance of the spacecraft. Now I'll briefly describe about the modes of operation. We have two main modes of operation. Each of them is designed to address one of the two main key goals that Eli mentioned. The first one is addressing the key goal about the supernovae, and this will be simply a survey mode. We're going to survey one of two pointing in the sky, each of them for 6 months. And we chose those. These are at near the ecliptic poles, and they were selected both in order to minimize the galactic extinction and zodiacal background, but in addition to have continuous visibility. So the limitations that I showed you about the Earth and Sun actually never within these 6 months limit the observation. So we can observe every 5 minutes for 6 months this pointing. We have, as I said, cadence of 300 seconds, and obviously also the antenna is not limited in this direction. So we have continuous download and analysis of the images. We set a threshold of 20 minutes alert between the exposure and data transmitted to the ground, to Weizmann headquarters, analyzed, and a transit event was detected and being sent. Again, this is an upper limit. The current estimate is of around 11 minutes. So this is really as real time as you can have. We do have in our documentation an alternative mode. This means that IAI will plan for that, and I'll describe it and then I'll say something about the working group. So in this survey mode, we can, around one of those, each of those pointings, observe up to 10 fields. And for each of them, we're going to observe for half an hour, move to the next one, and cycle through them. This will obviously give us a larger areas that we cover, but we pay you about the cadence and the continuous coverage. If you want to catch something, you might lose by that. But in some sense, one of the products of the working groups might be to convince that we should go into this alternative mode. So when you plan your desired or think about your desired science, you should try to compare those two. This is still our main survey mode, but where I would say open, it is open for discussion. Now, this observation will be interrupted basically only by, yeah.
So I thought that Eddie said that it would be the galactic poles. These are fields that are both galactic
no, these are ecliptic poles. He said galactic, but they are ecliptic.
But he said
It's
galactic,
not
and then he said that also that it's to avoid extinction.
Yeah, so still that in the ecliptic poles, even the south one, it's close to the galactic, and you have very low extinction. So, but they are the ecliptic poles and not the galactic.
What is the extinction?
What?
What is the extinction?
What is the value of the extinction?
Yeah, you said it's low. How low?
0.02, reddening, I think.
Iran,
We have it in.
I don't remember.
We don't remember by heart,
Hey.
but
You have to remember, you have a MATLAB.
yeah.
Yeah, but it's running on this.
If I remember correctly, it's the rating it's like 0.02 or something like that. But
I think that okay, let's see. The EB minus V of in this direction is like 2%, and
That's good enough.
but no, it's not good enough because it's
You need to
UV.
know what age.
It's roughly factor of 6, maybe.
So 10%?
Yeah, maybe 15%.
Because I mean, you're above the first ionization threshold of some elements, right?
Why is this related?
I mean, if you have neutral potassium or neutral sodium, isn't that going to absorb?
Yeah, but the galactic extinction has it's as a known, in most cases, as a very well-known dependency on wavelength. So it's the only strong absorption feature is near 220 nanometer, probably due to some silicate or
Silicates, yeah. The UV bump is from the silicates. It's not from potassium. Yeah.
In any case,
But-
it's extinction optimized.
yeah, first of all, it's both extinction optimized and visibility optimized, so we can actually observe continuously.
it's grasp optimized.
Okay, as I said, that we can interrupt those observations for TOOs, and again, the main goal here is to follow gravitational wave events and to detect the neutron star merger or the light. I would say that we are open for other TOOs, but this needs to be a very strong argument, I would say. We can observe 50% of the sky. This is some illustration showing the region that the sun cover, the Earth's cover, and the rest is what we can see. And we can, within 15 minutes, you can observe any place in this 50%, and for 3 hours. And as I said before, we're going to have still continuous transmission to the ground, except when we don't have the antenna, which is 13%. And we don't have any limits on the number of TOOs. And for each TOO, we can observe up to 3 hours, at least 3 hours, even without the power. You can see here some illustration about the expected error from a gravitational wave event compared to our field of view.
That's your best case scenario, right? When you have both LIGO detectors and Virgo, and not all events are going to be like that. So do you have a plan to scan
Like
larger?
2025, hopefully all of them.
So these are the predictions for in 2025.
I'm asking if you have a plan for larger error signals.
So
you can't cover the
we can do that, as I saw. There is no problem to do it. It won't be scanned. It will be observations. It won't be like a stewing thing. But you can cover a larger area again.
You can tie.
There is no problem of tiling this region. Yes.
You mentioned there is a human in the loop. Once you get an alert to actually commanding the spacecraft, there's a human in the loop.
So in principle, there is no human in the loop. We're gonna set automatic decision making, but obviously there will be some at the border, and those will be there will be a person deciding about the border line.
These will be throughout the hours of the day and the night.
Yeah, so we're gonna have, regardless of that, we're gonna have 24 hours mission operation both here at Weizmann and obviously at IIF.
The red phone.
So these are the main two modes of operation. However, before we actually, or I would say before, but at the beginning of the mission, we will have 6 months where we're going to have all sky survey. This is, I would say, the main driver for this is to have reference images for the TOO. So once you go to a TOO, you need to see that there wasn't anything else before there. And we're going to spend about 3 hours a day in the first 6 months covering the entire sky. This will be done using the TOO mode, again, in tiling. So this is in essence the same as you would do if you have a larger uncertainty of the gravitational waves. And it will be at least 23 AB magnitude. Actually, we're gonna be dominated by the confusion limit. It's still not clear to us where is this limit, but it's fainter than 23. And this means that a part of our transient survey, this will be the deepest map of the sky in the UV. Yeah, yes.
So, as Danny mentioned, there's going to be substantial leak from red sources. And as you mentioned in the slide about the PSFs, there's going to be a huge variation in terms of what image you get, depending on what part of the field, what part of the field of view you observe. So is there a plan to do this several times with different parts of the field?
So we have several ideas, but I think that Rana will talk about it later. Yes. We are very open. We are open to other ideas. One of which is just to have a fixed pointing. So every time that you're gonna trigger, you're gonna actually go to a fixed pointing and not center on the event. You can have tilings that are overlapping. There are several such ideas.
So there are two reasons to do this. This is one of them, and the second is proper coaddition. And there is, but for example, the steering. Yossi didn't mention, but the steering at this north near ecliptic pole regions, the satellite has to rotate due to the motion around the sun and to keep the solar panels direct to the sun. And this is so you will have basically natural rotation of the field of view, and it won't help with the first item you mentioned, but it will help with the second item I mentioned.
So this is almost my last slide. This is just a summary. I won't go into the details of the numbers. I just wanted to show you what is the ratio between our noise sources. We can see that the Zodiacal and Cherenkov are the dominant factor of our noise. Below that, we have the striate, and then all the electronics or the noise sources from the camera. And I'll leave you with this. I didn't try to be on time for tourism. First of all, I'm in charge, so I can do whatever I want. But I really thought that this is like an opening talk, that these are all the details that you asked before. And I'll say again, this information will be online, so you can either, by the way, send us an email and ask, as most of you did, or just find that there. Any more questions before we move to stocks?
Yeah. I have a question.
Yeah.
Ellie, I think explained this, but I didn't understand. So I'm just asking for a repeat, I guess. Why, if you had a Schmidt telescope with the same field of view in visible wavelengths from the ground, why couldn't you find just as many supernovae?
So first of all, I'll leave it to Avishai's talk. But the main thing that from the ground you have limitation. You cannot observe 50% of the sky. You can and you cannot do it continuously. So if you actually want to catch the rising part of the supernovae, you won't be able to observe all of them. And in addition, you have the UV part of measuring the radius that Ellie mentioned before. So these are two aspects that UV.
Let's several more. Let me two more, because it's a good question and very central. Yeah. So first of all, you have the day-night disruption, which cuts you by 50% on average over the year. The weather losses, even in good sites, probably require something like a 25% correction, at least addition on top of the 50% from the day-night. And on top of that, the background from the sky on the ground, even in good sites, and we don't have such sites in Israel, is much higher compared to the UV, even after all of those troubles that you just went into describing from space, which reduces your sensitivity per mirror size. So, and this is shown in this is the result of all of that is shown in that plot that we have. This is T, yeah. Right. So for a hot source, this is calculated. Right? Of course, it's not true for an infrared system, but for a hot source, after all of those corrections, the 30 centimeter effective 30 centimeter telescope in space is equivalent to a 6.5 meter mirror on the ground on the best site on Earth. So
and it's impossible to do a 6.5 meter telescope with such a large field.
Right. Yes. Now,
say possible.
Okay, if you give me all the money I need, it's possible.
You had another question, David?
Actually, it's a bit better because it's an old plot. I'll show you an updated plot.
And this is going to work.
What redundancies does the whole thing have?
So many parts have different redundancies. I won't go into those aspects, but if you start with the camera, first of all, by having 4 quadrants, then you might lose one of them, but still 3 will work.
Each one can work independently.
Yeah, yes. Moreover, you have some redundancies within this.
Which has their own electronics.
Yeah. So it's the same box, but it is controlled by a different FPGA, etc. So everything is redundant in terms of that, but moreover, even within the sensor, each part or some aspects have the triple redundancy. So you have 3 bits and you vote for them, and obviously you have in other aspects of the spacecraft, you have all your both memory and computer have dual, in some sense, dual computation, etc.
Yeah, the data links also.
Yeah. So the requirement for the entire mission is to have around 87 or 90% reliability at the end of life after 3 years. So this is actually what set the 3 years in that sense.
How about pointing
the reaction wheels?
No, the stabilization.
So we have 2 star trackers. So again, this is redundant, and in the reaction wheels, you have 4 reaction wheels, and that you don't actually need all 4. So we have at least 1 redundant, and in smart cases, you can actually use only 2. So
we can reach the requirements with only 1 star tracker.
Yossi?
Yes.
Hi. Can you go back to the PSF distribution slide? Maybe it's more a question to Sagi. I'm a bit worried about the on-axis chromatic aberrations. It seems that with maybe one more surface, you can get much better PSF on-axis, which will allow you for TOO at least better localization. Is that correct?
I allow Sagi to answer. I just say that we are really past the stage that we can modify anything on our spacecraft.
Too bad.
So this is not, but and again, Sagi can answer with additional surface. I don't think that you can reach the 80% optical transmission.
But regardless, you should.
Well, of course, at the expense of something, but maybe it's important enough because for TO you're after just one single event or source.
But you need the field of view in order to locate.
But you don't know where it is in the field of view.
Initially, right.
The error boxes are big.
Yeah.
Okay. Anyhow, it's too late, so never mind.
Any final question?
And they are only
Can I ask something?
Such a band, you're kind of in the limit. You are far in the regime of diminishing contribution from any additional optical element. The only thing that is still dominating here is chromatic aberrations. There are not that many materials that are transmissive in this regime. Basically, one of them we can't really use because of sizes complications, and we are already using the other two. So you are kind of at the lower limit that you can do for such a large field of view at this band.
Mm-hmm.
Unless you want to use with barium fluoride, but then it's very poisonous and everybody will die. It's always an option.
Not everybody.
Yeah, I won't.
So
Can I ask a question?
Yes.
Maybe you mentioned this pointing limit far away from the sun, the power limit. I'm wondering how much of the field of view is observable in parallel from the ground at the same time, and is it only from our region?
Yair, can you repeat the question?
Yeah.
Yeah, how much of the field of view is observable at the same time simultaneously from the ground? And is it only where the point on the Earth where the satellite is above, or can it be observed simultaneously from other places?
So this is a general observability. A TO can be anywhere. So you can, from each side, about 8% of the sky is visible if you don't have clouds. So if you don't have clouds worldwide, you can probably
No, I mean, that's a good question. The telescope in Hawaii.
No, there is no correlation. I think that he asked about correlation between the fact that the satellite is above the Canaries or whatever for west. It not as far as I understand, it's not have a strong correlations to the pointing.
No, of course not. You can be at the opposite side and then you can point anywhere.
Mainly by the sun. The fact that we are above Israel or above Canada doesn't matter.
The constant pointings are going to be changing from north to south exactly to maximize this ground visibility. And the rest is mostly dominated by the time of day. Right? Some time of day, nighttime in Israel, you can see it from Israel.
Photoshop will observe a place on the sky which is always bleak on the day side for as far as Hawaii is concerned.
No.
Why?
No.
Why?
There's no connection to it. Forget, we are like in some point arbitrarily.
So
We're looking arbitrarily on the sky.
Put the coordinates again for the locations. So as you can see, it's plus 66 or minus 66. This is going to be the dominant thing. So plus 66 is how to observe from Hawaii because Hawaii is at 20. So it's going to be low visibility, but not zero. When you go to minus 66.
But just to explain, this pointing will be observed 24 hours.
Yeah.
So it will be both when it's night in Hawaii and day in Hawaii. It doesn't matter where that we are in the far west.
If you really insist, plus 66, you can observe from Israel.
We can look from space towards the direction of Hawaii. It's okay. The Earth doesn't block us. Right? We're very far. And Hawaii can also look at that direction.
It's not completely
just
true.
not completely true, but almost. But the sun is there, right?
The real trade, if you want to point it out, is that we don't observe near the ecliptic. So when we observe at north, all the southern observatories are shut down. When we observe in the south, all the northern observatories are shut down. Hawaii is actually the best place because marginally it can observe both.